before starting on the implant, I just want to show you that there are two basic type of fixation which are used in orthopedics when we fix the bone. One is the internal fixation and the other is the external fixation. So we will be talking about the internal fixation part. The internal fixation mainly consists of plates and screws and the nailing system. And the external fixation is mainly the linear type of fixator, what we use the AO type of external fixator, and the ring type of fixator, that is the Elizaro fixator. So before starting, the basic unit or the basic thing which is used in the implant, the basic implant is the screw. The screw we define as the device, the mechanical device which converts the rotational forces into translation forces. So when we rotate with the help of a screwdriver, when we rotate the screw, it translates forward. So that is, the rotational force is getting converted into the translational force. Now we will discuss about the different types of screws. There are various classification they have divided into the screws. One is the cortical and the cancellous. So this one is the cortical screw which is used for the cortical bone fixation. This one is the cancellous screw which is used for the cancellous bone fixation. The cortical, the way of identify the differentiate is based upon the pitch and the thread depth. So if you see carefully, this is the cortical screw. The pitch is actually the distance between the two threads. So the pitch is low and the thread depth is actually the depth of the thread from the core diameter. So it is the thread diameter minus the core diameter or the shaft diameter. So if you see the cancellous screw, the depth is more in order to accommodate more and more cancellous bone to have an increased purchase of the screw, and the pitch of the screw is also more. The pitch is the distance between the two threads. So one is the cortical and the cancellous. This we have covered, that how to differentiate between the cortical screw and the cancellous screw. The another is it could be fully threaded or partially threaded. You can see here that this screw is, this and this screws are the fully threaded, that they have the threads throughout the length, whereas this is partially threaded, they have the thread only at the tip. Now they can be of two types. There could be 16 mm thread length or 32 mm thread length. Now the basic purpose of fully threaded versus partially threaded, the partially threaded screws are used for the leg screw. They are used as a leg screw for compression at the fracture site. For example, in the fracture neck of femur and other places where we need fixation in compression mode. Another classification is when we use the simple screw and the locking screw. If you see carefully, that this one is, just compare these two. So this one is actually a simple screw. This is simple screw and this is a locking screw. I will show you why it is known as the simple and why this is locking, because the locking screw have the threads over the head also. You can see here that the simple screw will not have the thread over the head of the screw. This is the head of the screw. Whereas in the locking screw, you can see they have the threads up to the head so that the screw gets fixed in the locking plate. So if I take any plate which is locking, the locking plate will have the threads over the hole also. Now this is the hole of the screw and you can see that the screw can get locked in this hole. So the main purpose is this is locking screw to increase the strength. We will talk in detail when we cover the plate. So just remember, the screws are cortical and cancellous, fully threaded, partially threaded, locking and the simple one. And another classification is the non-cannulated and cannulated, or we can say it as a solid versus cannulated. You can see that this is the solid screw and this is a cannulated screw because this has a hole in it so that the guide wire can pass through it. Again, this is used in the fracture neck of the femur or fracture scaphoid or fracture capitulum, where we need the exact, we insert first the guide wire and over this guide wire we check the position, and over this guide wire we insert the screw to avoid the multiple attempt of the screw fixation. So this is all about the screws. One more thing is left is the tapping and non-self tapping and self tapping screw. So again, this is, just see the tip of the screw. If you see this screw, this is having no flute. The flute is actually a longitudinal, this serration you can see. This is basically self tapping screw. This is non-self tapping screw. So in order to have a good fixation without tapping the bone, this screw has the mechanism of tap as well as. So this is the self-tapping type of screw, and this is the non-self-tapping type. So this all about the screws. Now we come to the plates. So the basic plate is actually, we start with the DCP. So these are the varieties of the DCP. This is the broad DCP 4.5 mm. This is the narrow DCP 4.5 mm, and this is the DCP of the 3.5 mm. We have the two system, that is the 3.5 mm screws, that is based upon the size of the screw, the diameter of the screw, that is 3.5 mm screw, and the 4.5 mm screw. So these two plates will have the 4.5 mm screws in their holes. So you can see that the 4.5 mm screw will get fixed to it, whereas this is the 3.5 mm and the screw will not go through this because this screw is 4.5 mm size. How to identify the DCP is, the broad and narrow are identified based upon the orientation of the screw holes. You can see that they have the zigzag pattern, that is the broad DCP, whereas this has the straight. The DCP usually have the screws and there is a spacing in between the proximal and the distal fragment. You can see here that there is no hole. It is for the fracture side. So the fracture side will come over here. These are for the one side of the fracture, that is the proximal fragment. This side is for the distal fragment. Like this they have divided, and this space they have left for the fracture side to accommodate. Now the principle of the DCP is the spherical gliding principle. Just see here, the holes of the plate are, for the screws, are oval in shape. They are not circular, they are actually oval in shape, and they are the combination of cylinder of inclined. The one is the vertical or the inclined cylinder and another is the horizontal cylinder. So we can say that in this cylinder the ball or this head of the screw will move like a ball. So when we insert it eccentrically on one side, it rotates, it moves. The ball moves from vertical to horizontal, and in this plane it can move. So what is the principle here? We fix the one fragment while the screw is in the central mode, or we can say it as a neutral mode. When we fix the screw in the center of the hole, it is the neutral mode, and the another screw when we fix in the eccentric mode, or we say it as a compression mode. So when we tighten while we keeping this in eccentric away from the fracture side, that is, we will insert the second screw in the opposite fragment of the bone over the screw should be in the eccentric mode. So we will fix it over here. The whole, this is the central mode or the neutral mode, and this is the eccentric mode or the compression mode. So when we tighten the screw will move towards the fracture side, and this will cause the bone to move towards the fracture side, and this will create a compression. So that is the mechanism how we get the compression here in the DCP. If we do not want the compression, then just insert the screw in the neutral mode, that is center, and all the screws should be in the center. If we want the compression mode, the one screw on this side should be in the center, the opposite fragment should be fixed in the eccentric mode, so that we can get a compression at the fracture side. So that is the principle, spherical gliding principle. How to identify? They are oval in shape in order to have a compression mode. Now what is the disadvantage of this DCP? The DCP and the under surface, if you see, the under surface is all flat. So when it goes into the plate, the plate, when it gets fit over the bone periosteum gets devascularized because of the compression. Because the under surface of the plate and the bone, in between the periosteum, it gets compressed, and the periosteum is mainly the vascular supply of the bone. So it devascularizes the bone. So for this, they have devised a low contact or the limited contact DCP. The limited contact DCP, I do not have in this table, but it is just the same as DCP. However, they have made a grooves over here. The empty spaces or the vacant spaces here in between the screws, they have created a grooves like you see in this plate. इस तरह के grooves बना दिए, so that when it gets over the bone, this much of the space or this much of the periosteum will be preserved. it will not get compressed. This is the basic idea of making the LC-DCP or low contact DCP. Now again there was a difficulty in LC-DCP also, because when you put screws, the screws can toggle. The screws can toggle like this, you can see. So this creates problem with the implant failure, this creates implant loosening. So in order to solve this problem, they have come with a new mechanism or a new plate, that is locking plate. So that's why the locking plate came into the picture. The locking plate basically has the mechanism of getting fixation of the plate or the locking of the plate with screws. So when you tighten the screw, it gets locked. The screw cannot move. So it gives them better stability, the better fixation, better purchase of the implant. So basically this is actually a combi hole plate. This is not exactly the pure locking type of plate. It has both the holes. It is a 8-shape hole. You can see that is a 8-shape hole. The one side of the hole is threaded, the other is non-threaded. And always remember, it is always towards the fracture side it is threaded, and away from the fracture side it is non-threaded. So this is the locking hole, this is the non-locking hole. So this plate can be used for both the purposes. If you want to have this plate for locking mode, just put the screw in the locking mode. This is the locking screw in the locking mode. And if you do not want the locking type of fixation, you just put the non-locking screw in the opposite hole or the non-locking hole. So this is the basic mechanism, while you cannot put the two screws simultaneously in the same hole. So you can use this plate for the locking type of mechanism when you need. The main indications of locking plate is the periarticular fracture, metaphyseal fracture, that is near the joint, or in the osteoporotic fracture where the bone quality is not good and you need a rigid type of fixation, a good type of fixation, so have a better purchase of the implant. And the third possibility is when you have a periprosthetic type of fracture, when you have the fracture near the prosthesis. So these are the basic indications of the locking plate. Now we have devised the numerous other locking mechanism for the anatomically particular region. For anatomical region like this, we have this plate. This is actually the distal femur locking plate. The distal femur locking compression plate. This is for the distal femur fragment. We have multiple options, 1, 2, 3, 4, 5, 6, 7. We have the 7 screw options for the distal femur fragment and this much of the hole in the shaft of the femur. So again, this is a combi hole. The locking and the non-locking screws can go in this. And always remember, towards the fracture side, that is this hole will have the thread, this hole will have thread, this hole will have thread. These are the locking. The opposite is non-locking. So this is the way how you identify the locking plate. Now one more plate is left, that is the 1/3 tubular plate. Now this is the 1/3 tubular plate. It is actually a semicircular type, or you can say it is a circular type of a plate. The cross section is actually a circular, 1/3 of a circle, and these are the holes which are non-locking. And the main indication is when you go for the fixation of small bones like ulna or like fibula, you can insert this type of bone. This is 1/3 tubular bone. Another plate which is not here is the recon plate. The recon plate is actually as the same as these type of plates, whereas they have the mechanism of getting, we can bend them in any direction in any plane. So the recon plate is mainly used for the particular difficult anatomical region where we want anatomical contouring of the plate, so we can use them. Now another set of plate. This is actually barrel plate, or you can say this is sliding hip screw plate, and this is the dynamic condylar screw plate. So this is DHS and this is DCS. The main mechanism, the main indication is intertrochanteric fracture. The DHS was mainly made for the fixation of the intertrochanteric fractures, whereas the DCS was made initially for the intercondylar humerus, intercondylar femur, the distal femur intercondylar part fixation. But however, they are now used for mainly subtrochanteric type of fractures or intertrochanteric type of fractures or valgus osteotomy, the DCS. The main difference between the two is the angle, that is the neck shaft angle or the barrel plate angle. This is the barrel, this is the plate, barrel plate. The main angle between the barrel and the plate is around 125 to 140 degree. So this angle is 125 to 140 degree, whereas in DCS it is 95 degree. So this angle is the 95 degree. So this is the basic difference between the two. Another plate which I want to have a look is this. It is same as DHS, however it has a extension of this plate over the greater trochanter. So this is actually a trochanter stabilizing plate. This is mainly used, the indication is where you have the comminution in the greater trochanter or the lateral wall of the greater trochanter, then you use this trochanteric stabilizing plate. However, this is now not being used. It is now going out of favor, mainly because of the PFN. Now the implant of choice for the intertrochanteric fracture, for unstable, for lateral wall comminution or for greater trochanter comminution, it is the proximal femoral nail which is the treatment of choice or the implant of choice nowadays. So this is actually the lag screw or the Richard screw. So this will go in this barrel. You can see that the barrel has the cannulation. So the screw will get fixed over the head of the femur and the neck of the femur, and the plate is going to fix in the shaft of the femur. So when you fix this and this, there is a play between the two, and this is the main principle, because now the fracture will get collapse in a controlled way. So we can control this collapse or control this compression, and this is known as controlled cancellous collapse. So that is the principle of the DHS. And the correct entry point or the correct site of entry of this screw is center and center. Center in the AP view, center of the head and neck, center of head and neck in the lateral view. But however, if this position is not, you are not going to achieve this, it is very difficult to achieve the center in the AP and center in the lateral, then it is posterior-inferior, which is the acceptable position. The posterior in the AP view and posterior in the lateral view and inferior in the AP view. So you should aim for the posterior-inferior aspect of the humeral or the femoral head. That is, the bone quality is really very great and you will get a good purchase. So that is the center, the first position of acceptance, and the second position which is acceptable is posterior-inferior. However, the superior and the anterior, that is the anterior-superior location or the anterior-superior quadrant of the femoral head should not be aimed upon, because there the cutoff chances, the failure rate of DHS or DCS is highest. The second thing you must know about the DHS is the TAD distance, that is the tip apex distance. So tip apex distance is actually, you measure the tip of the head of the femur and the apex, the tip of the implant and the apex of the head of the femur, the center of in the cartilaginous portion. If you measure this distance in the AP and the lateral view, it should be less than 25 mm. The sum of the TAD, AP and lateral should be less than 25 mm, then only it will not going to fail. If it is more than 25 mm, the failure rate of DHS is high. So this is all about the DHS, that is a sliding hip screw assembly. Just we remove them. Now we come to the picture of the nails. Now the nailing system. So these are the few nails which I have got here. Let's start from this end. This is actually the Ender's nail. The identification is it is a curve and it has an eye on one side. You can see there is a eye for removal of the implant. The Ender's nail was initially used for the pediatric fractures, the diaphyseal fractures of the femur or the tibia in the pediatric age group, but nowadays it has been replaced by a TENS system, that is the titanium elastic nailing system. But still nowadays it is being used. This is Ender's nail, just remember this. Now there is we go from for example, if we want to put in the femur, we will make an entry point over the distal femur metaphysis on the medial side and one on the lateral side. So in this way we are going to fix. Now if you assume that this is the femur, this is the distal femur, this is the medial side, this is the lateral side, we insert these two nails, we reduce the fracture, and at the fracture side these have the wide apart. The nails are wide apart and they are crossing in the proximal to the fracture side and the distal to the fracture side. So this gives a 3-point fixation in the fracture. So in this way the principle is 3-point fixation, and you can use multiple nails, 2, 3, 4 nails can be inserted depending upon the diameter of the bone and the nail. So that is the index nail. Now it has been replaced by TENS, the titanium elastic nail. Now this nail, when the nail was made first time, it was this. This is known as K nail or Kunstler nail. It was invented in around 1945 during the World War II by Kunstler in Germany. The basic idea of this nail is to give stability to the femur, in the fracture femur, and there is a incomplete type of nail, or we can say it as a hollow nail with a slot. Now this is the slot you can see, and the shape of the nail or the cross section is actually clover leaf shape. Now there is a plant which is clover, and it is not the clove, just remember it is a clover leaf. You can see here that this is the cross section of this, and this give a fixation in the medullary canal, the slot, and the slot opposite to slot is the eye. You can see that this is the eye on one end and on the opposite end. Now the basic mechanism or the basic principle of K nail is 3-point fixation. When we insert this in the femur, one at the end, the lower end, and in the middle is the isthmus. So it provides the fixation at 3 points, 2 at the ends and 1 at the isthmus. The isthmus is the narrowest portion of the medullary canal of the femur or any other bone. So it provides a 3-point fixation, that is 2 at the ends and 1 at the isthmus, the 3-point fixation. However, it does not provide any rotational stability. So it fails to provide the rotational stability, and that's why the interlocking nails came into the picture. Now, where should be the slot? Now, the questions which are being asked in pertaining to the K nail is, where should you place the slot? Always remember, the slot should be there on the tensile surface of the bone. So, the tensile surface of the femur is anterolateral. So, the anterolateral, the slot should go anterolateral side, and the eye will automatically go posteromedial, because the eye is diametrically opposite to slot. Now, the second question is, why there are 2 eyes? There is one eye at this end and another eye is this end. The basic mechanism, the basic function of the eye is to remove the implant. It is used for the removal of the implant. So if you are inserting this nail, why there is 2 eyes? Again, the examiner will ask you that why there are 2 eyes, one at this end and one at this end, because you are going to remove from one end. If this is the greater trochanteric end or the proximal end, if you have this nail and you are doing the implant removal, you just attach the hook over this eye and you will extract this. What is the purpose of this eye? So I will tell you, because this nail was initially or originally was devised for the retrograde nailing. So retrograde nailing was, you open the fracture site, you freshen the fracture ends, and you insert it retrogradely. So for example, if there is a femur fracture, you open the fracture site, you take the 2 fragments. In the proximal fragment, you just insert this, and once it is out of the greater trochanter, and then you reduce the fracture and then you insert it in the distal fragment. So this is the way how you do the retrograde nailing of the femoral fractures. So it is when you are going in the proximal fragment. So this eye goes into the proximal fragment bone, and now it got stuck. It is not progressing further. So in order to remove this nail now, this eye will be helpful, because through this eye then you can extract it again. So this is the purpose of the 2 eyes at the 2 ends. And another question is, usually they ask is, if you have the 8 mm size nail and the diameter you need is the 9 mm nail, and you do not have the 9 mm nail on the table, then what will you do? So you can combine the 8 mm nail through this slot. You can combine the 2 nails. I don't have the second nail, but you can combine the 2 nails, and now the effective diameter will be 9 mm. So that is how you can increase the one size by combining the 2 K nails. So this is all about the K nail. Just remember the 3-point fixation, the slot, the eye, why 2 eyes, and how to increase the size of the nail. So but the problem with the K nail is, the main disadvantage is it doesn't provide any rotational stability. So to take into account the rotational stability, to provide rotational stability, the interlocking nails came into the market. Now this is the interlocking nail, because it has the 2 bolts or the 2 holes in the proximal fragment and 2 holes in the distal fragment for interlocking, because the screw can go through these holes and it can fix the bone with the nail. So this provides a rotational stability. Now the nail is not going to toggle. Now the nail is not going to rotate. So this provides the rotational stability. And how to identify this nail? This is actually the femoral nail because there is no bend. As you see, this is the tibia nail. There is a Harjog bend in the proximal fragment. This is about 11 degree. And this is the nail which has the, you can see the convexity. This is the anterior. So this is anterior side. And this is the posterior side. So there is a slight curvature in the nail because to accommodate the curvature of the femur bone, because the femur is also bowed like this. So this is the femur nail. You have the two interlocking holes in the proximal fragment, two interlocking holes in the distal fragment. Now this one is the tibia nail. Now how to identify tibia? I have already told you that there will be a Harjog band of 11 degree at the proximal fragment because the entry side for the tibia is eccentric. Whereas in the femur, it is through the center of the medullary canal. But in the tibia, it is not through the center. It is eccentric. It is quite anterior to the center of the medullary canal. So to accommodate this eccentric entry point, they have made this band so that you do not perforate the posterior cortex while doing the entry. So this is the main mechanism why there is a band, and this is the tibial nail. Now, one thing in the femur, if you are going to do a femur with the diaphyseal fracture of the femur, you fix it with this nail. But if there is a fracture which is above this hole, if there is a fracture in the intertrochanteric region or the subtrochanteric region, this nail is not going to help because the holes are quite distal to the fracture. So for this mechanism, we have the proximal femoral nail, which has now replaced the DHS. So this is actually the proximal femoral nail, and they have a different type of screws for interlocking in the proximal fragment. So you can see here, now this is actually the proximal femoral nail. This is not actually the screw of this, but I have just to show you. There will be two screws in the proximal fragment. So this is the medial side, this is the lateral side, and this is of 6 mm and this is of 8 mm diameter, and again there will be two holes for the interlocking in the distal. So this is actually a short PFN. The size or the length is small. The long will be of the same as the femoral nail. The size will be the same. But this is the proximal femoral nail. There are two screws, the P1 and P2 for the proximal fragment, for the holding the fracture at the fracture intertrochanteric femur or the subtrochanteric, and the short PFN, the long will have the same as the femoral diameter. Okay, now we are over with this nail. After the nail